Our hero returns. With your exam.
Like 6 books.
Homework here. Very nice. Oh, nice.
My real section?
No.
L1. What? No. Time will pass off. But I never time schedule because I in the morning I attend one night. And I didn't attend one.
Okay, the exam seems harder this time. So there aren't that many people score above 90. So I just single out a few scores that are above 90 and give them out individually.
If you just leave. So why don't we have to divide this by?
It's run young gun, run yao gun.
So why don't we have to divide this by?
And then profan. Latin occurring. Swanango.
Seriously, we have to divide this by 1 period. But I didn't.
Where's the Uiuc? No? Okay, the rest of the examiners, those you can pass them out. Maybe Aditya can read them out, and then you come and pick up the exam from Aditya.
Adrian Biro? Who's Adrian Biro?
Meanwhile, I'm going to do the exam solution out of okay, I'll go through the exam solution.
Who's Andrew Bosch? Ariel Jalan.
Okay, let's go through problem 1. Okay, problem 1. I think this exam is quite difficult. The average is around 60 or so. 60 something. 61. And so if you do above 60, consider yourself very good.
That's like, drink this week.
Celebration.
Yeah, I think you said
Here. And then find the ODE. Okay, part A is to find ordinary differential equation for this.
Dan Jacob.
Okay, and if you switch the thing on, for t larger than 0, you just have to invoke kickoff voltage law. Ft must be L the IDT, which is the voltage drop across the first one plus Ri. So this is the ODE just in one line. You just write kickoff voltage law. The voltage across an inductor is L the IDT. The voltage across the resistor is R times I. And then when you switch this thing on, this is just kickoff voltage. And then you can also write other forms of this ODE, and you will still get the correct answer. And then part B, part C say that F1 of T is equal to sine of 2T. Okay, and then the output, this is the input. The output, I1 of T, is given to be 1/8 e to the minus RT over 2 plus root 2 over 8 cosine of omega t minus 3 pi over 4. Here, given that this is the solution, and that is the output, or that is the input, or this is the output, you're asked to find R. What is R in the second expression? What is omega in the second expression? Okay, find R and omega. And this is recognizing the first term. The first term is called what kind of a solution is the first term? The first term is called it. If you were to give a name to the first term of the solution, what should it be called? Not exponential solution, but something you learn in ODE. Two kinds of solutions. What? Homogeneous solution. The second one is a particular solution. The second one is driven by the source. Okay? And then this is the homogeneous solution. So, if you look at this ODE, the homogeneous solution is given by the fact that when you don't have a driving force. Okay? And you can solve for the homogeneous solution quite easily. It's something of this form. That is the homogeneous solution. Okay? So you look at this now. You're asked to find out what R should be. Actually, you're asked to find out what L should be. R and L should be. Okay? You're given this as one solution, and then you're given the second thing that when the input is equal to 2e to the minus 3t, okay, the output is equal to e to the minus t 4 t over L minus e to the minus 3t. Okay? If you look at this thing over here, it has this exponential form, and it has the same exponential form as this. This must be the particular solution. This must be the homogeneous solution. Okay? So, by comparing this one, you see that R over L is R over 2 in one case. Okay? And then if this is a homogeneous solution, you also get that R over L is 4 over L in the other case. So using these two equations, you can see that R must be 4, L must be 2. Okay, L must be 2, R must be 4. Just comparing the homogeneous solution part. So R is 4, L is 2. And then what should omega be? Omega should respond with the same frequency as a driving term. So omega must be equal to 2. So the answer is that omega equal to 2. These are the three solutions that the problem asks for.
Robert Master.
Okay. You can go. Is it you? Okay.
Okay.
So those are the solutions for part 1. And part 2, part 2 actually asks you to find the zero input response. What is the zero input response? Or I, zero input T. Okay, what should that be equal to? Well, zero input means that f of t must be equal to 0. Okay? F of t must be equal to 0 if there's no driving term. And if there's nothing there, either open the switch, there was nothing there, turn on the switch, should there be something there? There's nothing there, right?
Yin Wang.
Because nothing has been charged
How
up.
is Yin Wang?
There's no stored energy anywhere if there's no input to this system. Okay, so if Ft is equal to 0, you turn on the switch, nothing happens. So the Z I of t must be equal to 0. It is nothing that happens. Okay? And then with part 3, find steady state response. Find steady state response, yes.
I have a question about the previous one.
Yes.
Why don't you have to account for like the initial conditions? Because if there's no input, that means that the oscillating portion of the solution is on. So why don't you have to consider the 1/8 e to the r cubed?
The homogeneous solution should be there. Is that right? There is a homogeneous solution to this problem when you set Ft to 0. Okay, but you are also given the fact that there's nothing. There's nothing at all at initial time. When you switch on the switch, there's nothing that happens. Okay? So if you were to put in this homogeneous solution, I homogeneous solution is A e to the minus R t over L. Implies that A is equal to 0. Because of this condition. Okay? So there's nothing there. There's nothing there. So the homogeneous solution is not excited at all. It always is 0. Okay? Is that fair? Is that clear?
Doesn't it? It states that I1 is 1/8 times that. So how do you know that later on it changes? 0 means it has a sequence of
if you look at I1 of t, if you set t equal to 0, these two terms cancel each other. Because cosine of minus 3 pi over 4 is 1 over root 2 minus, with a minus sign, these two terms cancel each other. So this I1 of t does satisfy this condition. There was nothing there. There was no current that flows when t equal to 0. Okay, and similarly, when set t equal to 0, this is also equal to 0. I2 of 0 is equal to 0. Okay, so there's nothing there. There's no initial current that flows before you turn on the switch. Okay, so when there's no input, then the homogeneous solution is not excited at all. In both of these two cases, the homogeneous solution is excited because of the initial condition. This initial condition requires the homogeneous solution to be there. And also this initial condition, I1 of 0 equal to 0, requires the homogeneous solution to be there. Okay? But when there's no input, this initial condition requires the homogeneous solution to be 0. Okay, so the 0 input response is identically equal to 0. It's not 3. Okay? So the third part is a little bit tricky, and you have to understand what steady state response means. Steady state response means that if you let time becomes very large, all the exponentially decaying terms disappear. Okay? So this is t going to infinity transient response goes to 0. All the transients go to 0. That's what it means. So if you look at these two solutions, I1t and I2t, the only steady state response that remains is this one. Okay? I steady state t is equal to root 2 over 8 cosine of omega t minus 3 pi over 4. Okay, here omega is given to be 2 or found to be 2.
Did everyone get your paper?
Okay? So you're asked to find the phasor representation of this. The phasor representation of this then is equal to root 2 over 8 e to the minus j 3 pi over 4. Okay, so that is the I steady state response, the phasor that corresponds to this steady state response. The transients die out. Okay? Is this clear? The transients die out, leaving behind only the sinusoidal steady state sigma. The sinusoidal steady state sigma is cosine omega t minus 3 pi over 4, and that has the phasor representation given by that number over there. Okay? Let's move on to problem 2 then.
What's your name? Peter.
Problem 2, you're given a phasor circuit that looks something like this.
Everyone else?
A and then B. And then there is a resistor of 1 ohm. And then this voltage dependent current source depends on this voltage V1, plus or minus V1. And this is given to be 2 amps. Okay, 2 amps. You're asked to find the open circuit voltage of this circuit, open circuit voltage. Okay? And what should the open circuit voltage be? There is one thing that you should notice here, which is that well, I just follow the solution. Okay, you can do it umpteen numbers of ways. I just follow the solution that's provided, which is to replace it with the Thevenin equivalent. Okay, And that if you replace it with the Thevenin equivalent, it will look something like this. A voltage source, and then you put a 2-volt source here, 1 ohm resistor. So this part can be replaced with this Thevenin equivalent, and then the rest of the circuit you can replicate the same way. To V1, but this is still V1. Okay, and then you have this A and B. Okay, one thing to notice that if you have a current I1 flowing in this direction, I call this I3, and that this capacitor has an impedance of minus J. Okay, I will have I3 flowing this way. And let's assume that I1 is flowing in this direction, and then I have I2 flowing in this direction. And because of the fact that this is an open circuit, okay, so if I have I2 flowing this direction, that must also be I2. Okay, this must also be I2. And then I immediately see that there's no current flowing out of here. Okay, there's no current flowing out of here. Let me call this I4. I4 must be equal to 0 because this is the open circuit voltage. So I immediately know that I3 plus I2 must be equal to 0. Okay, I3 plus I2 must be 0 since I4 is equal to 0. And then from the second node over here, I must have I1 plus I2 plus I3 must be equal to 0 by applying KCL on this node over here. And then if I look at these two equations, it means that I1 must be equal to 0 since I2 plus I3 is already 0. So no current actually flows from this thing into this loop at all. So if this thing supplies a current, it's just going round and round like this. Okay? Nothing flows in from here. Okay? So you can calculate the open circuit voltage. The open circuit voltage would be V1. What should V1 be? If there's no current flowing here, V1 must be 2 volts. Okay? V1 must be 2 volts. Because I1 is equal to 0. Okay? And then you have to figure out what the open circuit voltage is, which is your V Thevenin. Okay, V Thevenin must be equal to V1 minus the voltage drop across this thing. So if the current is flowing in this manner, okay, if the current is flowing in this manner, then the voltage drop is equal to I3 times minus J, give you the voltage drop from here to here. Okay, so I3 times minus J must be equal to, or VT, V. So if this is going like this, then there's a voltage rise going in that direction. So V must be equal to VT plus V1 must be equal to VT. Let me see if I get the sign correct. VT must be equal to V1. Let me see if the current is flowing like this, I3 give rise to a voltage drop from here to here. So I have to subtract this voltage drop. So V1 minus this thing, okay, is equal to VT. Okay, but V1 is equal to V. No, sorry, this equation is not correct. I didn't finish this equation. VT is equal to V1 plus this thing. Okay? And then I have to figure out what I2 is. I2 is equal to 2V1. Okay, I2 is equal to 2V1. And V1 is just equal to 2 volts. Okay, so this must be 4 because V1 is equal to 2 volts. Okay? So I2 is equal to 2V1. But I2 and I3 are equal and opposite to each other. I2 and I3 are equal and opposite to each other. So I have Vt equals to V1, which is 2 volts, okay, plus J times I3, but I3 is given to be minus I2, so this would be equal to 2 minus J4, okay? Let me say, I have a sign error somewhere. What is that?
There's a negative J. I think it should be.
So this should be a plus sign over here. Okay, if I have a plus sign over here, then I2 is equal to minus I3, dt is this minus J3, and then I will have a plus over here. Okay, so I3 times this impedance, okay, give me a voltage drop from here to here. Okay, which means that V1 plus this voltage drop is equal to dt. That's fine. Okay, this is kickoff voltage law correct. And then dt is given to be this number over here. Okay. And then part B is going to be more difficult. And find ZT. Okay, find ZT. What is the Thevenin equivalence of this thing? And there are quite a number of ways you can do this. But the simplest way seems to be the test signal method. You can also use IN, or find the short circuit current, and then you have to solve a new circuit problem. And that seems quite difficult. So the simpler problem seems to be to use the test signal method. Okay? If you were to use the test signal method, you have to turn off the source. If you turn off the voltage source, what does it become? A short circuit, right? And if you turn off the current source, what does it become? Open circuit. So both of those circuits, if you were to use the test signal method, will look something like this. And I can put in a 1 amp current source with this thing and see what kind of voltage I get out of this one. This is still minus J. This current source is still 2V1, and this is still V1. Okay? So if I write down the Kirchhoff current law at these two nodes, okay, if I put back I1, I2, I3, I1, I2, I3, okay, and then I can put back I1, or this should be I2, and this should be I3, and because I have I1 flowing like this must be I1. Okay, you can write down Kirchhoff current law and Kirchhoff current law at the two nodes, okay? Maybe I just tell you the answer. The answer is that I2 is equal to 1 amp. Okay, I3 is equal to 2 amps. And then I1 should be equal to 1 amp. Okay, because I'm driving this thing with I1 is equal to minus 1 amp. Okay, if you plug this in, you find that Kirchhoff current law is satisfied here. Okay, I have 2 amps flowing here, or 1 amp flowing here, 2 amps flowing there. Okay, and then minus 1 amp flowing out there. And I find that Kirchhoff current law is satisfied there, and Kirchhoff current law is also satisfied there. Okay? And then you can find that V1 is equal to 1 volt. Okay, V1 is equal to 1 volt because of the fact that I have 1 amp current flowing like this. Okay, 1 amp going like this. Okay, V1 is equal to 1 volt. And then V1 minus 1 amp that's flowing through this thing, okay, times minus J, minus, must be equal to V. The V is the voltage at this point, okay, I'm going to find that V over there, okay, so V must be equal to 1 plus J. Is what I find V to be, which means that V Thevenin is just equal to 1 plus J. V Thevenin will be the voltage at this point which is driving the thing with the 1 amp current. Okay? And then Z Thevenin, oh, sorry, V is 1 plus J, so the Z Thevenin is 1 plus J ohms. Okay, there's a Z Thevenin. And then the part C, you're asked to find available power average of this. You can either remember the formula, P average is equal to V Thevenin squared over 8RT. Okay, you can either remember this formula or you can derive it. Okay, you know that the average power is always equal to half I squared R, or equal to half V squared over R. Okay, that is always the formula for the average power. But then, because of the circuit connection that you have this V Thevenin, and then you have VT, and then the Z load. What should Z load be for maximum power transfer? Okay, this should be equal to ZT conjugate. So finally, the inductive part cancel each other. The equivalent circuit that you have is just RT, okay, and then you have VT. If you look at this circuit by the voltage divider formula, then this is equal to half VT over 2 squared over RT. If you apply this formula to that, and then this will be just 1/8 VT squared over RT. Okay, which is that formula that you have. And then you have to figure out what VT is. VT has already been figured out over here. Okay, VT is figured out to be that. So VT magnitude square is equal to the magnitude square of this one, which is 4 plus 16. Okay, you find the magnitude square of this is this square plus this square, which is 20. Okay, RT, if you are given that ZT equals to this, what is RT? 1. Okay, so if you apply this formula, that would be 1 over 8 times 20 divided by 1, which is 5 over 2, right? 5 over 2 watts. Okay, so this is the power that we get. Okay, that is problem 2. Any questions on problem 2? Then let's look at problem 3. Problem 3 is my problem, so I think it's the simplest. So you're given this complicated looking circuit, Vs of t, with a inductor, capacitor C1, L1, the resistor R1, and then capacitor C2, and inductor L2. And then you're asked to find V out of t. And you're asked to find the transfer function, which is defined to be V out, the phasor response, over Vs, the phasor response. Okay? So we can convert this into a phasor circuit and treat this very much like a resistive network. So first we like to find out what the impedance of this part is. Z1 would be equal to 1 over j omega C1 plus j omega L1 plus R1. Okay? And then Z2 is just a parallel connection of it. If I call this Z1, Z2, Z2 is the parallel connection of that. So it can be written in very many different ways. It can be written as the j omega C2 plus 1 over j omega L2. There's another way to write the parallel connection of these two. You add their admittances and then invert them. The admittance of the capacitor is given to be that. The admittance of the inductor is given to be that. You add them and you invert them. That gives you the